Hi, my name is Nick Borson, and in this video I'm going to talk about indices. No, I don't mean the Dow Jones or the S&P 500. This is a programming channel, so I'm really talking about uh, numbers that represent a position in a sequence. So, for example, an index might be representative a character, the position of a character in a string, or the position of an item of an element in an array. Or it could just be a position in some sort of abstract sequence that isn't necessarily objects in memory, but just some sort of conceptual sequence of items. So in this video, I'm going to cover the concept of zero-based indexing, meaning that you number the items in a sequence starting at 0 as opposed to 1, and why that's often used in programming. And I'm going to talk about different ways of specifying ranges. So an index would be just a single item in a sequence. A range would be a range of items in a sequence. And I'll go into talking about off by one errors, which are a common class of programming error, where it's very easy to, if you reason incorrectly, to end up with something that's just off by one. And finally, we'll go into a code example to show how indexes work, or indices work in practice. Okay, so let's talk about zero-based indexing. Now, in ordinary life, we're very used to one-based indexing, where we just number things starting at 1. It's even baked into our language. We say, first, we talk about the first, second, third, and fourth items, etc., in a sequence. So it's the way ordinal numbers work, right? We start with 1, 2, 3, and go onward, or first, second, third, and go onward. But in programming, we often use zero-based indices, where the first item has index 0, and we count up from there. Now that may seem kind of counterintuitive just because we're so used to numbering things starting at 1. It's even, like I said, baked into our language. With zero-based, we have to say the first item is index 0. But it does have the nice property that the index is just the distance from the start of the sequence. So you could think of the index of an item as the number of items before it, or the distance, in terms measured in number of items before it from the start of it, from the kind of the origin of the sequence. And that, in fact, is why array indices are often zero-based in most programming languages, because it's just very efficient then to compute the offset in memory from the start of the array to an item with a particular index. You just multiply the index by the size of each item. On the other hand, consider how we number years on a calendar. We're, of course, used to numbering years starting with 1. Because that's just the way that calendars were designed. They weren't designed by programmers. But what if programmers had designed our calendars? So in real life, of course, we use one-based indices. So we start with the year 1 AD. And then when we want to number centuries, that means that the years 1 through 99 are the first century. The years 100 through 199 are the second century. The 19th century then is the 1800s. Not the 1900s, and the 20th century is the 1900s, not the 2000s. So, everything is kind of a little off by 1 compared to if you just naively think, oh, 1800s would be 18th. Oh no, 1800s, that's the 19th century. So using one-based indexing kind of throws that accounting off. And it's even worse than that. You notice the little asterisks I put there. If we number the centuries that way, it means that the first century is only 99 years. It's not a full century. So some people argue, actually, that the first century is the years 1 through 100, and the second century doesn't start until the year 101, and goes from 101 to 200, and that the current millennium didn't start until the year 2001, for example. So some people who are very pedantic like to say that. None of that confusion exists if programmers had designed our calendar and we use zero-based years. We would start our calendar, or we would start our numbering with the year 0 AD and count up from there. Century 0 would be the years 0 through 99. Century 18 would be the 1800s. Century 19 would be the 1900s. Easy peasy. So even though the numbering starting with 0 is less familiar than the conventional way of doing things starting with 1, it does make reasoning about things often less confusing. All right, we've talked about zero-based indices. Let's now talk about ranges. So an index refers to a particular item in a sequence. A range is just a way of referring to some number of items, some number of contiguous items in a sequence. For example, maybe you have a string and you want to refer to a substring, some sequence of characters within that string. And there are three basic ways of specifying ranges. The first is to use a start index and a count. The second is to use the index of the first item and the index of the last item. So that's what's called an inclusive range, because both the first and the last indexes, or indices, refer to items that are included in that range. And the third way is to use an exclusive range, in which the range goes from the first item up to, but not including, the last item. All of these are valid, but the important thing is not to confuse them. In particular, it's important not to get mixed up between inclusive ranges and exclusive ranges. And one way to keep that straight is to use naming conventions that allow you to tell them apart. So if the indices are first and last, that's probably an inclusive range, because last would be the index of the last item in the range. So the last item is included in the range. Whereas if you have begin and end, that's typically an exclusive range. So particularly in C++, the C++ standard library, the standard template library, has this convention of using begin and end, of representing a sequence of items, or a range within a sequence of items, using begin and end iterators, where begin is the first item in the sequence and end is one past the last item in the sequence. So that's an exclusive range. And another name for, sometimes you'll use min and max, which is like the minimum value and the maximum value in the range. So that would be another example of an inclusive range, because the max item is included in that range. So those are ranges, three ways of doing it. And I'm going to show you some code that actually uses ranges, and we'll see how to use all three ways of doing that at the end of this video. But first, let's take a look at a little table here to kind of show you how these different ways compare. So here I have at the top, I have a sequence of 10 items numbered 0 through 9. So those are the indices of the individual items in that sequence, zero-based indices. And I have three ranges kind of just shown graphically here. There's an empty range at the very beginning, so it's like kind of positioned right before the first item. A range of length 4 starting at index 3, and another empty range at index 8, so just before the item 8 in the sequence. So if we want to use the first index plus count convention, then the empty range at the beginning is represented as the first index is 0, or the start index is 0, and the count, of course, is 0. In the second range of length 4, starting at index 3, we have 3 and 4. So the start index is 3, or the first index is 3, and the length of the range is 4. So the number of items in that range is 4. It makes sense. And then we have another empty range starting at 8. So again, we have the start index of the range is 8, and the range is an empty range, and so it has 0 items in it. So that's pretty straightforward. That is kind of the convention used in the .NET framework for sometimes. For example, like in the string.substring method, which returns a substring within a string. It takes start index and count parameters to represent the index of the first character in the substring, and then the length of the substring. Okay, so let's say we want to use an inclusive range instead. Now, empty ranges are a little weird with inclusive ranges because, for example, let's look at that first empty range. It's at position 0. The start index is 0. But if we had 0 as both the start index and the end index, that would not be an empty range, because that 0 item would be included in the range. So in order to show an empty range, we actually kind of have to make it inside out. We have to make that the last index be -1 in this case. It has to be less than the first index. So that's a little odd. So typically I tend to avoid inclusive ranges for cases where empty ranges are a possibility for that reason, just because it's a little odd. Although it works. I mean, that method works. It's just a little strange. The range of length 4 goes from it includes items 3, 4, 5, and 6. So for an inclusive range, we just say 3 and 6. 3 is the index of the first item, 6 is the index of the last item. And then we have another empty range starting at 8. And again, the last index has to be less than the first index, or 1 less than the first index, in order to represent an empty range. For the exclusive range, the first empty range is 0, 0, because both the begin and the end indices are 0. It's an empty range, and that means it's an empty range because the index is 1 past the last item. Or another way of saying it is that if you can take the end index end index subtract, so end minus begin, or the end index is like the distance. Let's see, the distance between begin and end is the size of the range, if you will. So end minus begin is the length of the range. So in this case, of course, it is 0 for an empty range. For the range of length 4, it starts at index 0, and the end index is 7. It's one past the last item. So it includes all the items from 3 up to, but not including 7. So 3, 4, 5, and 6, but not 7. And again, the length of that range is 7 minus 3, which is 4. And again, the last empty range, starting at index 8, it goes from 8 up to, but not including 8. so it's an empty range at that location, and its length again is 8 minus 8, which is 0. So those are some examples of ranges. Before looking at some code, let's take a quick moment to talk about off-by-one errors. This is kind of a class of errors that involves just getting mixed up about, if you get mixed up between inclusive and exclusive ranges, for example, you can end up where you're off by 1 because you've got the right idea, but you've kind of mixed up whether the last item is included or not included, and so you end up off by 1. And there are various ways you can end up with off by 1 errors. So here, for example, let's take a look at these two for loops. Which one of those loops executes 10 times? So the first loop, we initialize the integer I to 0. We execute the loop as long as I is less than 10. And after each iteration, we increment I. So for the first iteration of the loop, I will be 0, which is less than 10. For the second iteration, it will be 1, and then 2, and then 3, and then 4, and then 5, and then 6, and then 7, and 8, and then 9. And then after that, after the iteration where I is 9, we increment it to 10. 10 is not less than 10, and so we follow the loop. So the loop will execute for I 0 up to, but not including 10. So that's kind of an exclusive range there, right? And 0 up to, but not including 10 means the numbers 0 through 9. And so that is 10. That means that loop will execute 10 times. The second loop there, from 0, I equals 0, I less than or equal to 10, will execute from 0 up to, but and including 10, which means that loop actually executes 11 times. Another kind of interesting class of error, off-by-one errors, is called fenced post errors. The analogy is, let's say you have a fence that's, say, 50 feet long, and there's a fence post every 5 feet. How many fence posts do you need? Now you might think, okay, well, I could just divide 50 by 5, and it means I need 10 fence posts. But actually that's off by 1, because it's not accounting for the fact that you need 1 post at the beginning, plus a post for every 5 feet of fence. So you're always going to need at least 1 fence post. If the fence is only 5, and one way to reason about this is to consider the case where the fence is exactly 5 feet long, and you find you don't need 1, you need 2 fence posts, 1 at the beginning, and then 1 at the other end. And then if you add another 5 feet of fence, you need another fence post, and another 5 feet, another fence post. So it's 1 plus the length of the fence divided by 5. Of course, if it's not an evenly divisible by 5, then you also have to include an extra fence post for the remainder that's left over. So you can also err in the other direction. So let's say that you're looking at a list of items separated by commas, and you have, say, 10 items. How many commas do you have between those items? Well, you only have 9, not 10, because you don't have a comma after that last item. So those are examples of off-by-one errors, and it's just important to think carefully about whether you're off by 1 in certain cases, and we'll see an example of that as we dig into our code example. Enough of slides. Let's take a look at some code. So here I have an example. I've written a little example program where I've done 3 different implementations of the binary search algorithm, and that algorithm basically is using a sort of a divide and conquer approach to find an item and find an element of value in a sorted list or sorted array. And it's sort of the same technique that you use when somebody plays a guessing game, like I'm thinking of a number between 1 and 10. What is it? And you say, well, 5. And they say, higher. Okay, 7, higher. Okay, 8 or 9, lower, and so on. And so you narrow down on it. You don't just go from 1 up to 10. You start in the middle, and you kind of divide. You sort of divide the search space in half each time with each guess. So binary search works like that. And so at any given time, there's kind of a range of positions in the array that we're searching where the item we're looking for could be found. And each guess we make, we pick an item in the middle, we compare it with the value we're looking for, and if the value we're looking for is less, then we can narrow our search range to just the items before the one we looked at. And if our value we're looking for is greater, we can narrow our search range to the items after the one we're looking at. So there's this concept of ranges comes into play, and so I've implemented this with 3 different ways of representing ranges, using the index plus length approach, the inclusive range approach, and the exclusive range approach. So first, let's look at just kind of the test. Here's sort of the test code that calls our binary search. So I have an array of strings, and these have to be because binary search only works with things that are sorted, because we're for obvious reasons, I guess. I mean, it only works to kind of divide and conquer like that to narrow down your search space if you know that the items are in order. So I just pick some arbitrary strings that are in order. And also I want to make sure that the search works if you are searching for a string that's not in the array. And so here's some searches that are not in the array. Searching for any of these should return -1. So my binary search function returns the index of the item that it finds, if it finds it, and it returns -1 if it doesn't find it. And then I have some test code here. So here we are, we search for a particular string in the array, and we're passing in the index we expect that string to be at, which could be -1, and if it's different, then we output an error message. Here is our overall search thing. We have an binary search interface that has our function, our code, and for each string in our array of strings, we try searching for that string, and we expect to get back the index, the actual index of that string. And then we have our missing strings, and for each of those, we search for it, and we expect to get back -1 because none of those are in the search thing. And we search using all 3 of these methods. So I have defined an interface. Let's see now, where is that? Well, let's see now here. Okay, so index length. So here is the interface. So we have defined an interface that has just a binary search method on it, and that interface is implemented by my index length class. And so here is our first implementation of the binary search function. So it takes an array of strings, it takes the value we're looking for, and then it's going to search using this divide and conquer method to try and find the location of that value within the array. So what we start doing is we define a range that encompasses the entire array. So we're using here a start index and a length to represent the range. So the start index is 0, and the length is the length of the array. And then for each iteration of this loop, we are going to compare the value we're looking for with the item in the middle of that range. And either we find a match, or we know that the value we're looking for is either before or after that item, so we can narrow our range by half to only include the items either before or after the item we just compared with. And if we get to the point where we've narrowed our range down till it's an empty range, then we know that that item does not exist in the array, and we return -1. So our while loop has the condition while length is greater than 0, while the range is not empty, we can keep searching. And so the first thing we do here is we calculate an index in the middle of the range. So to do that here, where we have a start index and a length, we just take start index and we add the length over 2. And that is an index somewhere in the middle of the range. Now, if the length is an odd number, like in this case, then it'll be exactly the middle item. If the length is an even number, then it's either going to be, you can't really have, there is no middle item. You can either be the item just after the middle or the item just before the middle. In this case, it will work out to be the item just after the middle, but either way, that's fine. It's worth noting that, we're dealing with integers here. So integer division work, it always is going to return another integer. So length over 2 is always going to round down. Okay, so now we compare the value we're looking for with the array element at that index, or middle index, if you will. And this compare function is going to return either a negative number if value is less than the middle value. It's going to return a positive number if value is greater than the middle value, or 0 if they're equal. So if n is 0, then we know that the value we're looking for is before the middle value. So we narrow the range to include just the elements before I. Well, how do we do that? Well, the start index is still going to be the same, but the length is now going to be I minus start index. So if you think about that, that means that for example, let's say that we are in this 0, 1, 2, 3 case, right? So the length here, by changing the length to 2, that means that it's going to include 0 and 1, but not 2. Okay? So start index is the item that we've just compared with is excluded from that range. Here, it's a little more complicated. If n is greater than 0, it means the item we're looking for, it comes after I. So we need a way to figure out, to narrow the range to adjust the elements after I. Well, it's easy enough to figure out what start index should be. It's going to be I plus 1. But now we have to figure out what the length is going to be. In order to do that, I computed the index 1 past the last element in the old range, which is end index. So essentially, this is like going to the exclusive range approach here. So you computed the element 1 past the end of the range, and then I update the start index, and then I update the new length is going to be the end index minus the new start index. Okay, so that's a little tricky using that approach, but it works. And of course, the other case, if n is neither less than 0 nor greater than 0, then it means we actually found the item, so we return that index. If we fall out of the loop, that occurs if we've narrowed down our range to the point where we know that the item's not found, and in that case we return -1 for not found. So that's index plus length. Now the same exact algorithm works for, let's say, the exclusive ranges. Well, let's do inclusive ranges first. Same exact algorithm, but we just have a slightly different way of representing ranges. So here we have the range is an inclusive range, so the first index is, to start with, we want the entire array. So the first index is 0, and the last index is the index of the last item, which is at length -1, because length is the number of items. Well, the item at that, because with zero-based indexing, the item at length is going to be 1 past the n. The last item is going to be at length -1. And then each iteration, we iterate, the logic is the same, but we no longer have a length member. Instead, we have to detect an empty range by determining if first is less than or equal to last. Remember, if first is equal to last, that is not an empty range if we're using exclusive ranges, because that means that index, first and last, is the same value. That item, that index, is in the range. So when we get an empty range, that only occurs when last is less than first. Okay, so again, we compute the index in the middle of the range. In this case, so we have to do the little trick. This is a little tricky here. So we take the first plus last minus first over 2. So that's going to end up rounding a little differently than the last time, but it still works. So so let's say, for example, that we have the range from 0 to 4 inclusive, right? So both item 0 and item 4. So first is going to be 0, and 4 is going to be, last is going to be 4. So if we take last minus first, that is 4 over 2, which is 2. So it's going to be the middle item. If we have an even number of items, let's say 4, we have that would be 0 through 3. So last is 3. Last minus first over 2 is going to be 3 over 2, which with integer division, as rounding down, is going to take us to 1. So that works out fine. So so we've computed the index of the middle item, which could be off, either before or after that kind of middle when there's even number of items. Again, we do the comparison same as before. If n is less than 0, it means we narrow the range to just the elements before I. So last is now I minus 1. And if n is greater than 0, we narrow it to the range just after I. So first is now I plus 1. So this is actually relatively simple in the exclusive range case. And if we found the value, we just return its index. And finally, let's look at the exclusive range case. So here we have, instead of first and last, we have begin and end. So begin is 0, and end is now array dot length. So one past the last item, one past the last index in the array. And then again, each iteration. So with the inclusive range, we said first is less than or equal to last. Here we say begin is less than end, because if begin is equal to end, that would be an empty range. Again, we're computing the index to the middle item. We do it the same way, basically, we did with the exclusive range. The rounding in this case goes the other direction, but that's fine. So n minus begin for exclusive range is the length of the range. So we divide that by 2 and add it to begin, and we get the index of the middle item. Again, we do the comparison. Now, if n is less than 0, it means we need to narrow the range to the items before I. So we set end is equal to I. Not to I minus 1, but to I, because remember, end is equal to 1 past the last item. So I minus 1 would be the last item in the new range, but we actually want to be the end to be I. So because the new range does not include end, and we want I to be excluded from that range. Now in the other direction, if we want to narrow the range to just the elements after I, we set begin to I plus 1. So there's kind of a little asymmetry here because of the fact that the begin is included in the range, but end is not included in the range. So it's important to get that right. This is an example of where you could have an off by 1 error if you didn't carefully think through what you mean by this. And again, if we found the value, we just return its index. So if we run our program, we find that there's let's just run it here. Find that there's no output because, in fact, all of the test worked fine. All the strings that we expected to find were found, and all the strings we didn't expect to find were not found. Okay. Well, I think that pretty much sums up what I wanted to say about indices. Indices are super important in programming because it's how you often refer to things in a sequence of items, and there are tons of things that operate on sequences of items. And it's very important to learn to think carefully about these cases about exactly what an index means, and in particular whether it's 0-based or 1-based, or whether ranges are specified as inclusive or exclusive, and so on. Otherwise, you can end up making mistakes where you are off by 1. So I hope that was helpful, and thank you for watching.